Swayam Prabha. Digital India. Educated India.
So, today we have seen the analysis of a Jeffcott rotor with a disc is offset from the center of the shaft or the mid span of the shaft, and in this particular case we derived the equation of motion. Also we have seen the procedure to obtain the unbalanced response. Now, because the degree of freedom of the system is 4, because we have 4 equation of motion, when we obtain the response with varying speed, if we vary the speed and solve the unbalanced response for various speeds, we will find that wherever there will be coincidence of the speed with the natural frequency of the system, there will be critical speed, and these can be plotted. That means, the amplitude of the response and the speed can be plotted, and we can able to see that we will observe 4 critical speed in this particular system, as against in the previous case for the Jeffcott rotor only 1 was there, and because rotor is symmetric in 2 plane, so it is 1, but here we will find that now it will be having 4 critical speeds. Till now we have considered simple rotor, in which case mainly we have considered the flexibility of the shaft, but we have considered the bearing as rigid. In some machines the rotors are relatively rigid, but bearings are more flexible, and in such cases the rotor or the shaft can be considered as a rigid body and is mounted on some kind of flexible support. For such analysis, obviously we need to have a different analysis as compared to the Jeffcott rotor model, and in the present lecture we will consider not only the flexibility of the bearing, also the support or the pedestal flexibility, how we can able to study the effect of these flexibility onto the especially we are interested in the critical speed of the shaft, how it is affected due to these flexibility. Now, let us see the overview of the presentation. So, we will be considering the rotor as rigid, and we will be mounting that rotor on simple anisotropic spring as bearings. Anisotropy will be in this particular case of the spring will be there, that in 2 orthogonal direction the stiffness property will be different, and even we will be analyzing apart from the critical speed of the system, how these how this particular motion gives forces to the bearing. Now, how much forces are getting transmitted to the bearing, that also we will be studying. Some of the concept which we will be seeing in this is elliptical orbit of the rotor, translatory and conical whirl motion of the rotor, even phenomena like forward and backward whirl of rotor. So, some new phenomena we will be studying in this particular rotor system. So, we will start with a rigid rotor. We know rigid rotor is having in general, a rigid body is having in general 6 degree of freedom if you are not constraining it in any of the direction. But for this particular case, we are constraining the motion of the rotor in the axial direction, as well as because it is spinning about its own axis of rotation. So, total degree of freedom will reduce by 2 for this particular case. So, this is a rigid rotor and it is supported, let us say, by spring at ends in two orthogonal directions. In this particular case, we can able to take, let us say, axis z along the direction of the rotor, vertical axis is y, and we have x axis in this direction. This particular rotor is spinning with omega, and during analysis we are considering again the synchronous whirl condition. That means the whirling frequency of this will be equal to the spin speed of the shaft, and this is the bearing axis or shaft axis. C is the geometrical center of the shaft. In this particular case, the G is here, let us say, that is offset in the radial direction, that is by ER, sorry, this is offset in this axial direction by EZ, and offset in the radial direction is also there, that is ER. So, we have not only the radial eccentricity, but also the axial eccentricity, and because of this not only we will be getting the unbalanced force, but also we will be getting the unbalanced moment. So, in this particular case, let us say the centrifugal force is acting at G is m e omega square. Now, as we can able to see, the rotor can have up and down motion. So, we will be describing that by x and y, and also it can have tilting about x axis and y axis. So, we will be representing that by these angles. So, basically we have 4 degree of freedom system, and for the angular displacement, let us see the sign convention. So, this is the bearing axis, this is x axis. So, according to the right hand rule, if we have x, y, z, so x to y, y to z, z to x. So, in this particular plane, we should take z to x as positive direction. So, that means, if we are interested in the shaft center line, so this is the shaft center line. So, tilt is phi y, this is the positive direction, z to y, z to x. The same shaft in z y plane would be taking this direction as positive. This is the phi x angle, and this will be the positive direction of the angular displacement of the shaft in the y z plane. So, basically, if we see this particular rigid rotor, it is having a linear displacement in vertical direction, that is y direction, also is having horizontal direction, and apart from this, it is having tilting about horizontal axis x and vertical axis y. So, these are 4 degree of freedom which will be requiring for the motion of this particular shaft. And in this particular case, as we have considered the spring, so let us define the spring stiffness kx, ky, kx, ky. So, these springs are spring in which, if we are applying this particular rotor, let us say for this particular rotor, if we are applying a vertical force at the center of the shaft, we expect only the linear displacement in that particular plane, and if you are applying a horizontal force, then it will be having motion in that plane. If you are applying a couple at the center, this will be having pure tilting. So, it will tilt about its center. Also, if we apply moment about the vertical axis, it will tilt about that in that particular plane. So, as such, the bearing property which we have considered at present, they are such that all the 4 degree of freedom are uncoupled. That means, we can give to this particular rotor the vertical motion, translatory motion independent of other motion. Similarly, in horizontal plane, and if you are giving a tilting, so there is no translatory motion, only pure tilting is taking place. Similarly, in the other plane. So, that means, in this particular case, if we want to analyze the rotor, we can able to give various motion independent of each other. So, in this particular case, we can able to give the motion independent to each other. So, let us say I am giving a motion to the rotor purely in the y direction. So, I am giving this particular displacement to the rotor, and this particular displacement is y. So, because of this, what will happen to the spring? They will get stretched, and because of that, it will give a force at ends to the rotor. And apart from this, this is the center of gravity position. So, we will be having force in x direction as centrifugal force, this one. This force we can able to see separately how this unbalanced force is coming. So, let us see in xy plane the rotor. This is the center of rotation, this is the center of gravity, and we have elastic force in y direction and x direction. So, this is y direction, because 2 springs are there. So, it will be twice of this, and in x direction 2 k x, and centrifugal force is acting m e omega square. Our reference axis for time is x axis. So, this is omega t. So, you can able to see the component of the force in x direction is m e omega square cos omega t, and component of the unbalanced force in y direction is m e omega square sin omega t. So, this particular component we have taken here, this is unbalanced force in the y direction, and we have defined the axial eccentricity as E z. So, this is the position of the so C is here and G is this location. So, now you can able to see if we do the force balance in y direction, we will get the equation of motion like this 2 k x y y. Then we have these forces are opposite to the displacement direction. So, negative. Unbalanced force is in the positive y direction. So, there is, and then it should be equal to the inertia of the rotor. So, it should be equal to inertia of the rotor. So, from this we got one equation of motion, that is m y double dot plus 2 k y y is equal to m e omega square sin omega t. On the same line, if we draw the free body diagram of the rotor in other plane, that is z x plane, it will be easy, it will be on the similar lines. We can able to obtain equation of motion like this. So, instead of sin omega t, we have force f x me omega square cos omega t. So, that term will be coming here. So, these are two equations of motion which we obtain by giving two independent motion in y direction and x direction. Now, we will see the tilting motion. If you want to give tilting motion to the rotor, let us say in y-z plane, z is the bearing axis and y is the vertical direction. For this, we need to have direction y to z for tilting of the rotor. So, let us say rotor is tilting about its center. So, this angle is phi x and the springs are at the ends. So, the spring which is attached here will give force in the downward direction, because that will get stretched. Here it will get compressed. So, it will give a force opposite to the compression, and you can able to see that this particular distance is the actual compression of the spring. And if we take the total length of the rotor as L from here to here, total length of the rotor, then this angle will be L by 2, this distance will be L by 2 into phi x. So, compression of the spring will be this much. So, we can able to calculate the force, spring force into this deformation. Here also same force will be acting, because rotor is symmetric. L is the total length of the rotor. Now, you can able to see there are two forces acting opposite to each other, and apart from this, if center of gravity is here, there will be centrifugal force. This will be same as the previous one, m e omega square sin omega t. Now, we can able to do the moment balance of these. This distance is E z, radial eccentricity of the axial eccentricity of the rotor. Now, we can able to write the equation of motion. So, now I am taking the moment balance. So, we have from unbalanced force, this is the force into the moment arm, that will be E z, that is acting counterclockwise direction opposite to the deformation direction. So, it is negative. Then from the bearing support, you can able to see this force and this force will give a couple in the counterclockwise direction, that is also opposite to the deformation or the angular displacement, which is in the clockwise direction. So, this will also be negative. So, we will be getting k y L phi x, this is the force into the moment arm is L, should be equal to I d phi double dot in x, because it is tilting about its diameter about x axis. So, this will be the rotary inertia. So, this equation we can able to write it as phi double dot x plus, let us say 0.5 phi x k y L square is equal to m e omega square E z sin omega t. So, this particular moment balance we obtain in y z plane. Now, similar expression we can able to get in the z x plane, that we can able to write directly now. So, in that particular plane, the angular displacement is about y axis, and so these expressions can be written E z, then instead of cos omega t will come here. So, this is the third and fourth equation of motion of this particular rotor system. And now, all these four equations, these two and the previous two, we can able to write in a matrix form. the 4 equations which we obtained, if we see carefully, all these equations have been obtained by giving displacements in x direction, y direction and 2 angular direction independent of each other. As such, our assumption was there is no coupling between these motions. So, these motions are also uncoupled. So, if we are looking into the equation, let us say in one of the direction, x direction. So, this contain only the x variable, y is not appearing. Similarly, if we see the second the equation of motion in y direction, it does not contain y. Apart from y, it does not contain any other variable. Similarly, other 2 equations in the they are not containing x and y, but they are containing a single variable. So, these equations can be solved independent of each other. So, if we let us take one of the equation in the x direction first and try to solve it. So, we have equation of motion mx double dot plus 2 kx x is equal to m e omega square cos omega t. The solution we can able to assume as cos omega t because there is no damping we considered. So, this can be the same phase as the force, this one. So, if we substitute this in equation of motion, we will get capital X plus 2 kx capital X cos omega t term will be common. So, you can able to see this will get cancelled and we can able to solve for x, that will give us m e omega square divided by 2 kx minus m omega square. Think here double m is coming, only single m will be there. So, this is one of the solution. On the same line, you can able to see, we can able to write the equation for y like this, only the subscript of stiffness will change. Now, looking into these 2 equations, the solution will be x cos omega t, and that means we can able to write this as 2 kx m e omega square cos omega t. Similarly, y we can able to write it as sin omega t because there the forcing is sin omega t. So, response also will be sin omega t. So, this is the response. So, let us say this is 5th equation, this is 6th equation. Now, the 5th and 6th equation can be combined. If we square these equations and add it, we will get let us say I am squaring this and this. So, basically this will give me cos square omega t plus sin square omega t, that will be 1, and this equation is nothing but equation of a ellipse. So, that means in this particular case we expect the rotor, if we want the x and y, if we want to plot it, rotor will be having elliptical path. The rotor center will be moving in during the whirling. So, this is the during whirling, this will be the orbit, and where this distance is the capital X and this is the capital Y. and this ellipse orientation will be along the x and y direction. So, this ellipse is not inclined because we have taken the spring system simple in this for this particular case. We will look into this orbit in more detail. Let us first see the critical speed of the rotor. So, we have the response here. So, you can able to see if this particular denominator becomes 0 for a particular value of omega, because here kx is a constant for a particular bearing, m is constant, and omega is a variable which is the spin speed of the shaft that we can vary. If we are increasing the speed continuously and if we are finding that this denominator becomes 0, that means we can able to write that separately. 2 kx minus m omega square is equal to 0. So, that is a particular speed which we call it as a critical speed, and that critical speed will be given as root 2 kx by m. This is the one of the critical speed. If we put the denominator of the second expression corresponding to the y displacement, we will get another critical speed, that is second critical speed. The expression for that will be root 2 ky by m. So, you can able to see that we are getting one critical speed here, another critical speed here. We got two critical speed. Till now we have considered only the equation of motion in the x and y direction. Till now we have considered the equation of motion in the x and y direction, but we have not considered the equation of motion in the phi x direction and phi y direction. So, we expect another two critical speed corresponding to that direction. So, let us obtain them. So, let us take equation of motion in one of the plane corresponding to the angular displacement. This was one of the equation of motion, and if we take the solution of this, let us say a capital phi x and e j omega and same as sin omega t, because there is no damping. So, response will be with the same phase as the force, and this we can able to substitute in the equation of motion to get this equation. This is a capital phi x capital phi, sorry, this is phi y, all are phi y, sin omega t will go from both sides. Now, we can able to write the phi y equal to m e omega square E z. E z is the axial eccentricity, E is the radial eccentricity which we wrote as E r. So, we can able to write this as 0.5 k y L square minus omega square I d. So, we can able to see on the same line we can able to write the amplitude in other direction by just changing the subscript of the stiffness coefficient in x direction. I d is the diametral mass moment of inertia of the rotor. Now, again we can able to see if these denominators are 0, we will get critical speeds. So, I am equating the first one equal to 0. So, I am calling this as third critical speed. So, this will give me critical speed, the third one, equal to 0.5 ky L square divided by ID. Similarly, from here we can able to get the fourth critical speed, that will be 0.5 kx L square by ID. So, we could able to get 4 critical speed. Apart from this, if we see the solution which we assumed here for k for phi y, for phi x the solution will be of this form, and they can be combined. These two expressions can be combined on the similar way as we combine in the x and y direction by squaring them and adding them like this. So, this will give us this capital phi is the amplitude and small phi is the time dependent term. So, that means in this particular case also we are getting the equation of an ellipse. We will analyze this motion carefully, how this will be. So, in both the case, in the linear case and the angular displacement case, we got that this displacement is giving some kind of elliptical motion. So, let us try to see this motion how they would be, how it will be elliptical. So, first is the translational motion. So, both translation motion we can able to consider simultaneously. So, if this is the rotor, rigid rotor, so what is happening? This particular rotor is having only pure translation motion in x and y direction. It is not tilting and it is whirling. So, is not only it is spinning about its own axis, but during that is whirling. So, whirling path is basically this particular path. If we see from this side, this particular path is elliptical. So, this is the motion which we obtain as ellipse path x and y direction. So, this will be the elliptical path. So, not only it is spinning, but also it is whirling, and whirling the motion is in the ellipse. The second motion of the tilting, pure tilting is tilting about its center, and so it will be something like this. The center remains stationary and ends are moving, and ends are moving in an ellipse. So, if we see this particular path of the end, this will be moving in ellipse. So, if we see from the side, again it will be having elliptical path. Not only it is spinning about its own axis, but also it is having conical motion about its center of the shaft. So, let us see this particular motion. So, here the first graph you can able to see, first picture, that we have a translatory whirl. The rotor is spinning, let us say in the counterclockwise direction, and is whirling in an ellipse. The direction of that is also I have shown as counterclockwise direction. That means I have shown both whirling direction and the spin direction same, but not necessarily they will be same. But here initially I have shown that is they are same. We will see for some condition this whirling direction and the spin direction may be different. So, that means if you see this the third case in which the spin direction is still in the same counterclockwise direction, but whirling direction is clockwise. So, that means the shaft is spinning in one direction, and in the first case is also whirling in the same direction. Second case, shaft is whirling in the same previous direction, but now it is whirling in the opposite directions. So, these two cases we can able to call as a synchronous translational whirl or anti-synchronous translational whirl. Similarly, if we see the conical whirl, in conical whirl the shaft, let us say, is rotating in the counterclockwise direction, and the ends of that, if we see, they are having conical elliptical path, but they are having the same counterclockwise direction rotation. So, this is synchronous conical whirl motion. And so, basically if you see, each and every particle of the shaft will be having same motion, elliptical, may be different magnitude, but sense of the rotation will also be same. This is another case in which this conical whirl is there, the spinning is in the counterclockwise direction, but whirling is in the clockwise direction. So, this particular case we call it as a anti-synchronous conical whirl. In this particular case, the spin speed direction and the whirling directions are different. Now, we will see for these two kind of translatory and conical whirl, when it will be, that is synchronous whirl, when it will be anti-synchronous whirl, those analysis we will see in detail. So, for that we are assuming some quantities, like we are assuming the stiffness of the spring in x direction is less than the y direction, and because of this we will find that we define the critical speed corresponding to the x direction as first critical speed. So, we will be having first critical speed less than the second critical speed, which we define for the y direction whirl. Now, I am taking a one case in which the rotor speed, which is omega, because these critical speeds are fixed for this particular rotor system. The spin speed or rotor speed we can able to vary. So, let us say this rotor speed is, first we are operating below the first critical speed. For this particular case, let us see what will be the whirl direction. In this particular case, let us again see the expression for the displacements which we derived earlier. So, this was 2 k x minus m omega square cos omega t, which was we wrote as capital X cos omega t, and y is m e omega square 2 k y m omega square sin omega t, which we wrote as capital Y sin omega t. Now, because now we are rotating at below the first critical speed, so that means you can able to see that if we substitute, we can able to rearrange these equations such that we can able to write this as m e. If we take out, let us say, m from denominator, so we will get this as first critical speed square minus omega square cos omega t, and y as, if we take out m from the denominator, so it will cancel from the numerator. So, we will be having this as second critical speed minus this. So, with this expression we can able to see that when the omega is below first critical speed, this capital X, which is this quantity, and capital Y, which is this quantity, both are positive. So, for this particular case, X is positive, also Y is positive. If we see the orbit, that is elliptical orbit, let us say this is the elliptical orbit. So, we at time t is equal to 0, we can able to see, if we are substituting the time t is equal to 0, y is 0, that means, and x is having maximum value, that is equal to x. So, at t is equal to 0, y is 0, but x is capital X value. So, that means this position here y is 0 and x is having maximum value. So, at t time we are here. Now, after some time t, if t is some finite value t1, what will happen? Both quantity, this x and y, will be positive, because for small variation in the time, this will be some finite value positive, this will also be finite value positive. Capital N and capital Y, we already seen they are positive. So, we will be having both x and y for some time t is equal to t1, these both are positive. That means, from here we can go this side where both x and y are positive, because this is a positive quadrant. So, you can able to see that in this particular case with time we have this particular direction of the world, okay. And in this particular case we have considered the direction of the omega also as counterclockwise, so that you can able to see that the whirling direction is also counterclockwise and the spin speed is also counterclockwise direction. Basically, here we have a rotor which is moving. So, this is the path of the rotor during whirling, and at time t is equal to 0 it is here, at some finite time it becomes it approaches here. So, not only it is spinning about its own axis in the counterclockwise direction, but also is whirling. So, we saw that for this case, when we are rotating the rotor in below the first critical speed, and this for this particular condition in which I think the second critical speed is more than the first one, we have the forward or the synchronous whirl condition. Synchronous whirl condition, both are having same direction of whirling. Now, let us see the second case in which now we are operating the rotor between two critical speeds. In this particular case, we will see that in the previous slide, when we are here, when omega is more than the first critical speed, this quantity, which is capital X, will be negative, and this quantity, because this is more than the first critical more than the omega, because omega is in between the two critical speed. So, this quantity will be positive. So, in this particular case x is negative and y is positive, and again if we see at time t is equal to 0, this is 0, y is 0, and x is, this becomes 1 at time t is equal to 0, but x is negative. So, when we want to plot the orbit of the shaft, let us say this is x direction, y direction, at t is equal to 0, x is negative and y is 0. So, y is 0 and x is negative, that means it is only possible when we are at time t is equal to at this position, because no other position the at x is equal to negative, y is 0 except this position. So, at t is equal to 0 we are here. Now, at time t is equal to t1, again we will go to the equation, we will see that these two quantity, this become positive, this remains negative. but they will become some finite. So, they will not be 0, and for that particular case we will see that x remain negative, y becomes positive, and this condition will prevail if we are moving from here in upward direction, because here x is negative and y is positive. Here is not possible because both x and y are negative. So, only possibility that after time t1 this will reach here. So, that means you can see now is whirling in the clockwise direction. The spin direction we have not changed. The spin direction is the previous one, counterclockwise direction. This is the spin direction, this is the whirling direction. So, you can able to see that for this particular case, when we are operating the rotor between two critical speed, we have anti-synchronous whirl condition, and in this particular case the rotor is spinning in one direction, but is whirling in opposite direction. Now, consider a third case when we are operating the rotor at above the second critical speed. For that case, what happens? So, this third case is when rotor is above the second critical speed. In this particular case, x and y both will be negative, that we can able to see, because now omega is greater than both. So, capital X and capital Y both will be negative. So, at time t is equal to 0, x is negative and y is also negative. So, if we see the orbit, both are negative. So, this is the position. Sorry, y is 0, again I am repeating. Okay. So, at time t is equal to 0, x is negative, y is 0, because it contains sin omega t term. So, that means we are starting with this position. For time t is equal to t1, x remain negative, y is negative now. So, the only possibility is it will occupy this position at t is equal to 0 here, and at t is equal to t1. T is equal to t1 here. So, that means you can able to see now the rotor start whirling in the same direction as the spin speed, that is counterclockwise direction. So, in this particular case again rotor will start whirling in the same direction. So, we will be having synchronous whirl condition, but here we will be having because of negative sign, we will be having this 180 degree phase between the response and the force. So, we have seen that how a rigid rotor which is supported on an anisotropic bearing having stiffness property different in two direction can give rise to 4 critical speeds, 2 related with the translational motion of the rotor and 2 related with the tilting or the there is a rotational displacements. In this particular case, we have not considered the axial vibration of the rotor, also we have not considered the torsional vibration of the rotor, only the transverse vibration we have considered. In this, we have observed that the path of the shaft during whirling, when we consider, let us say, pure translation, it is an ellipse. Also, when we are considering pure rotating this tilting motion, that is also ellipse, but that is in conical world. So, first corresponding to the translational world and another is the conical world, and in both cases each and every particle of the shaft execute a ellipse. And we have seen that as we change the speed For linear case, we have seen that when we are changing the speed, the direction of the world changes. When we are below the critical speed or in between the two critical speed and after the third critical speed, the whirling direction changes. The same analysis is valid for the conical whirl also. There also on the same line we can able to say that when we are operating the rotor below third critical speed, we will be having synchronous whirl, and between third and fourth we will be having anti-synchronous whirl, and after fourth critical speed again it will become synchronous whirl. So, in this particular lecture we have seen very interesting concept of the whirl, especially how it changes its direction when we change the speed. So, in the today's lecture we have seen analysis of a Jeffcott rotor, but the disc was offset from the mid span. In the Jeffcott rotor case, we had 2 degree of freedom system, that is because there was no tilting of the disc. So, we had equation of motion in 2 in numbers. So, we expect 2 critical speed in that particular case, but because shaft is symmetric, so effectively we get 1 single critical speed in that particular case. In the present case, when disc is offset, we have seen that it is a 4 degree of freedom system, and we expect 4 critical speed from this, but because of the symmetry in 2 plane, that means in the vertical plane and horizontal plane, effectively we will get 2 critical speeds only, and this particular wobbling motion in this again I am repeating the last sentence. So, in this lecture even we have seen the wobbling motion or the tilting motion of the disc, and in subsequent lecture we will see that this wobbling or the tilting motion along with the spinning gives gyroscopic couple also, and in subsequent lectures we will analyze those motions also.